Hello everyone, my name is Christian Steinmetz and I'm a PhD student at Queen Mary University of London, working with Josh Rice. Today I want to talk to you about our work, ronn, Randomized Overdrive Neural Networks. So you may be aware of audio effects, which are tools that musicians and audio engineers use in order to shape sounds. And they can use these to create all different kinds of effects, things like distortion, reverb, delay, compression, and many more. And they're really a core component of what makes all of the timbre options available to musicians today. So how they basically work is that we have some input audio signal, that could be your guitar, it could be someone singing or speaking, and then you pass it through this device that has some controls or knobs that let us shape the sound, and then we get some new version at the output. And recently there's actually been a lot of interest in modeling audio effects with neural networks. And that means trying to emulate the effects that a traditional effect is doing using a neural network. And the way you would do this generally is by having some data set of guitar recordings, for example, and playing them through a audio effect to generate an output. And now this gives us an input and output pair to train our neural network. So then we simply insert the neural network and then we train it by computing some loss between the target process signal and the output of our neural network, back propagating to update the weights of the network. And recently there's been a lot of success with these approaches, trying to model a ton of different types of audio effects, as you can see here. For more details on that, check out my review here. But the real problem with all of this is that, well, one, they don't help us design new effects, and they also require that we have this data, that we kind of record the data from the audio effects, which can be really costly and cost a lot of time as well. And it also requires that we train the model, we have to do this training process, which really, takes a long time and can be also very compute intensive. So we were asking the question then, what if we could design new audio effects that are interesting without any data and without any training at all, which really sounds maybe somewhat crazy. But this is what we achieve with ronn, which is randomized overdrive neural networks, as we call it. And the way we do this is we start with a basic temporal convolutional network, or TCN. As you can see here in this diagram on the left, it's just composed of one-dimensional convolutions followed by an activation, and we can stack as many of those blocks together as we want. Then what we do is set the weights of each layer to be random values, and we can sample from different distributions, we can use different initialization techniques. They all will have a different impact on the sound we get. Then what we find is that the parameters of this network, the kernel size, the dilation, the activation, the number of channels, those all become controls that the user can use to adjust how things sound. And by passing some amount of audio into this TCN, we'll get some processed version out. Now you might think that this would be just garbage, but in reality we found that you could get some really interesting sounds. And so interesting, in fact, that we built an audio plugin that works in real time to process the audio using these temporal convolutional networks that are randomized, and using Juice and PyTorch, we're able to now build this plugin so it can be used by audio engineers and musicians inside their digital audio workstations. And you can see here on the UI that we've included these different elements here, these controls like the kernel, the channels, and all of that, so that audio engineers can directly interact and produce new audio effects. Now, how does it sound? We found that there were some clear correlations between parameters of the network and how things sounded, where shallower networks produced strong overdrive and distortion effects, and deeper networks produced really interesting reverb, delay, and even drone-like sounds in really interesting ways. We also found that the activation functions had interesting impact as well, with sigmoid kind of sounding more harsh and aggressive, with ReLUs, on the other hand, sounding smooth and rolled off. So there's a lot of experimentation that can go on there. Now let's go to a quick demonstration and hear some of the examples. Thanks so much for watching. The paper, the code, more demos, as well as the plugin yourself that you can download and try out are all available here at ronn.ml. And if you have any questions, we'd be more than happy to answer them. Thank you.